Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. Today I want to talk about Stokes' theorem for manifolds, which is a beautiful generalization of the fundamental theorem of calculus, Green's theorem in a plane, and also Gauss's divergence theorem. It's a very, very important theorem in the theory of manifolds, and to motivate it, I want to just begin by reminding ourselves of those baby versions of this theorem. Okay, so one version that we've seen before is what happens with line integrals. So suppose you have some manifold y and you have some oriented curve c, which goes from a to b. So remember, we can talk about line integrals on this curve. So to do that, we need a one form. So suppose we have some function which is smooth. So f is in c infinity y. Then we get a one form by considering df. And if you take the integral of df over this oriented curve, what does it equal? It just equals f of b minus f of a. In other words, you just evaluate this f at the endpoints and you subtract, and that gives you that integral. Okay, so this is a wonderful theorem. This itself generalizes the fundamental theorem of calculus. In that case, the curve that you look at is just an interval inside the real line. And the form that it takes is the integral of some derivative type quantity. It's the integral over some curve that's related to that function at the endpoints of that curve. So the next thing that Stokes' theorem generalizes is Green's theorem in the plane. So let's remind ourselves what that's about. Okay, so suppose you have some domain you can integrate in the plane like this D here. And then what you can do is you can look at the line integral around the boundary. Okay, so you look at the outside and look at that line integral, the integral over the boundary of D, of some one form, so p dx plus q dy. Okay, so normally in a several variable calculus course, you look at this more as a vector field. Okay, and then what happens is that you can rewrite this line integral as an integral over this two-dimensional domain. And what is that integral equal to? It's the integral of the curl, dq dx minus the p dy. So just to see how these are in a similar sort of format, let's have a look at this formula more closely. Here you have the integral over the domain of some derivative type quantity. In this case, the derivative type quantity is the curl. And then that's equated to an integral of the original thing over the boundary. Okay, here's an integral of some derivative type quantity over a curve, and you're looking at some integral which now is just an evaluation over the boundary of a curve, which is just the endpoints. The third thing that I want to show you and remind you is the divergence theorem due to Gauss. Here, instead of looking inside the plane, we look in R3, some domain that you can integrate. So let's look at the surface of this domain where you can integrate. Okay, that'll be the boundary of this D, and you can look at the surface flux. Okay, the surface integral f dot n ds. Okay, so that turns out to be equal to what by the divergence theorem? It equals the integral over the whole of that three-dimensional domain of the divergence of f. And this here you can also see has the same sort of format. Okay, so you've got some vector field here, and essentially you're just integrating that over the boundary, and it's related to the integral over the whole domain of some derivative type quantity. Okay, so now we can state Stokes' theorem. I'll state it as it is so that you can see the analogy with what's written here, and then I'll explain the terms later. Okay, so to start off with, we'll have some k-dimensional oriented manifold X. And inside there, we'll consider some regular domain D. So that's supposed to generalize, for example, the domain that you integrate here inside R3, or such a region inside R2 that you integrate, or a curve inside here like that. Okay, so it's going to be a generalization of that, and I'll make that more precise later. We also integrate forms. So suppose omega is a smooth k minus 1 form. Then Stokes' theorem is a beautiful formula which combines all of these three baby versions. Okay, and let me just show you here what it is. So if you look at this regular domain D, okay, you can look at its boundary, and I'll tell you what that is later, but the key point is that that's some part of a k minus 1 dimensional manifold. So you can integrate a k minus 1 form there, and that will get you some number. So we can perform this integral over the boundary, and that equals the integral of some derivative type quantity, this d omega, which I will define later, and it's the integral over all of d. Okay, so this beautiful formula, this single formula here, which has a very simple sort of presentation, is going to incorporate these three examples. And in fact, this one here, you can see, is very similar to what we have in this case here. Okay, so for the special case where f is some smooth function, okay, so it's a zero form, then you can look at df and the integral along some curve, okay, and then what is f itself is just a function, and to integrate along the boundary of the curve is just 2 points, and then in that case all it means is just this difference here. Okay, so to make sense of the formula in Stokes' theorem here, we need to define firstly the region that we're integrating, so that's going to be a regular domain, so we have to define what it means to be a regular domain. Also, what is the boundary of such a regular domain? And finally, given a k-1 form omega, what is this k form d omega? Okay, so let's start with the notion of a regular domain. And the picture that you should have in your mind is like this, just as when you look at the Green's theorem in the plane and also Gauss's divergence theorem. Okay, so you should think of a regular domain as something like this. So more precisely, the definition is as follows. Suppose you have a closed subset D of your manifold X. Okay, we're going to say it's a regular domain if it satisfies this extra condition here, which is essentially a condition on the boundary. Okay, so what is that extra condition on the boundary? So we check at each boundary point P. Okay, so P will be on the boundary like this. It's on the boundary, and so by boundary I just mean all the points in D which aren't in the interior. So basically the condition is that you have a nice chart around that point P, and it's a chart which describes the part of D as just the upper hemisphere. Okay, so I'll make that more precise. So we're going to assume there's some open neighborhood of this point. So U, there's our U here. And there's going to be a chart, so an oriented diffeomorphism of this U with a unit ball. So it's a k-dimensional ball here. And let's suppose this k-dimensional ball has variables x1 up to xk. Okay, so that's going to be isomorphism with U. And we're going to assume that what's the part of U that corresponds to D? Okay, so the intersection there, that's this part here. Okay, when you pull it back to the unit ball, it should correspond to a part of that unit ball, and we want it to be the upper hemisphere. Okay, so this phi inverse of D intersect U, which is a part of this unit ball here, is the locus precisely where the last coordinate xk is greater than or equal to 0. Okay, so that's the definition. So one thing to note about the definition, and this is important, is, well, what about the bit where xk equals 0? Okay, of course, that's going to be the boundary. So here, this xk is greater than or equal to 0, all that shaded black region here. It's also blue shaded. And the bit where it actually equals 0 is, of course, has to be the boundary here. So it gives you a description of the boundary. And what's more, it even gives you charts on the boundary. So that's the reason why this definition is set up the way it is. Okay, so this is the important remark. Okay, so of course, we here want to integrate over the boundary, so this boundary should be a manifold, or at least some region of the manifold that you can integrate over. So let's just see how this is. So the boundary of D, of course, it should be one dimension lower. It's going to be k-1 dimensional now. Okay, so it now has charts. So what can you do? Well, we can restrict this map here to just the portion where xk equals 0. Okay, so if you look at the k-dimensional unit ball and look where xk equals 0, you just get the k-1 dimensional unit ball inside there. Okay, so when you restrict to this, what's its image? The image, as I just remarked before, is just the boundary of D inside this open set. So it's the intersection of U with this boundary. And since you have these charts for each boundary point, that means that you have a manifold structure. Of course, the fact that these are diffeomorphisms, okay, means that these all patch up nicely with smooth transition functions, and in fact they're going to be oriented as well because we assumed this is an oriented diffeomorphism, and hence we get a structure of an oriented manifold on the boundary. Okay, so we've defined a regular domain and also its boundary, so we can work out that part of the formula. It just remains to state what is d omega. So this is an operation, this d, called the exterior derivative. Okay, so let me just introduce some notation first. So I'll let EKX denote the space of smooth k-forms on X. And the theorem that we have here is the following. I won't prove this theorem. We actually have a well-defined linear map from EKX, the space of smooth k-forms, to the space of smooth k+1 forms. Okay, and it's going to be like a differentiation. So remember, what is a smooth k-form? It's a linear combination of things of this form, okay? K-forms are the forms, some smooth function g times df1, which df2, all the way up to dfk. And from that, I need to give you some k+1 form. And all you do to that is you keep the last part and you just apply d to this. So dg is a 1 form. So you have dg, wedge df1, all the way up to dfk. Okay, so let's just look at a special case of this. When k equals 0, of course, you don't have these f part. You just have a single function here. That's a 0 form, it's just a function. And if you apply d to that, you get dg. So it's what you think it is. It's the usual differential map here, okay? And this formula generalizes this in a very natural way. The other point to note is, in what sense is it well defined, okay? So what do you have to check? So remember, given any k form, you can express it as a linear combination of this in lots of different ways, okay? And it doesn't matter how you express it as such a linear combination. If you use this formula, you always get the same k+1 form on the other side. So that's the exterior derivative, and that's the last ingredient to make sense of Stokes' formula here. I want to now show you how Stokes' theorem here for manifolds simultaneously generalizes both Green's theorem in the plane and the divergence theorem. Okay, so let's have a look at Green's theorem first, where we're integrating over some domain D inside the plane R2. The object we're integrating is some one form omega p dx plus q dy. So in Green's theorem, we have the line integral, the contour integral around this boundary of D of this one form. And then over here we have the surface integral of the curl. So let's see what this d omega is, and what we want to show is that it's going to match up with the curl. Okay, so here's our omega, and we want to look at d omega. And what was the formula for that? Well, we looked at how to define it on terms like this, and we just extend linearly. So here it's dp wedge dx plus dq wedge dy. That's how we defined the exterior derivative. So let's work out each of these two terms individually. Okay, so to do that, what we do is we re-express this dp in terms of dx and dy, using the usual change of variables formula. So dp is just what? It's just dp dx times this dx plus dp dy times this dy. And we'll wedge that with dx. And of course, this is a wedge product. It's a distributive, so you can do this term wedge this plus this term wedge that. And the thing that you note here is you have a dx wedge dx. And since they're the same, and by the definition of how we did the wedge product, of course, that term has to be 0. Okay, so that's part of this alternating multilinear algebra fact. Okay, so that part is 0, and all we're left with is this wedge product here. So it's just dp dy times dy wedge dx. Okay, so that's what this dp wedge dx is equal to. You can do the same thing with dq, and again, the part that has the dx there would remain, so you get dq dx, dx wedge dy. But the part with the dy, when you wedge it with the dy, gives you a 0. So that's all you have left for dq wedge dy. And now you just have to sum these two things together. Right, there's a dx wedge dy here, so you've got dq dx of them, but you've got a dy wedge dx here. And if you remember the way we defined this using determinants, it's alternating, so when you switch them back, you have to change the sign here. So you have a minus dp dy times dx d wedge dx dy coming from this term over here. And of course, if you look at that, you see this d omega. What is this? It just gives you the curl that you see in Green's theorem. So this left-hand side is just the contour integral that you see in Green's theorem. And this right-hand side is indeed just the surface integral of the curl that you see in Green's theorem. And Stokes' theorem generalizes Green's theorem in that way. Okay, so let's see what happens with Gauss's divergence theorem. So in Gauss's divergence theorem, you normally write it with some vector field, so we'll use a similar notation, f. Okay, and the vector field will be given in terms of the usual tangent vectors ddx, ddy, ddz, so p ddx plus q ddy plus r ddz. And of course, we want to convert this into integrating forms. And it turns out that the one corresponding to this is the following, and this is not too hard to believe. Omega has to be equal to this 2 form, okay? So this is something I guess you want to integrate on a surface. It's the boundary of some domain in R3. So this should be some sort of a surface integral. Okay, so to do that, we need 2 forms. And it's the following one here. So corresponding to ddx is dy wedge dz. So you have p dy wedge dz. Corresponding to ddy, you have dz wedge dx. So it's the terms which don't involve the y. You have q of them, and plus finally r dx wedge dy for the ddz term there. Okay. And there are various reasons why you can see that this is the correct thing to do, but I guess the most important thing is that it will give us the correct answer and reduced to the divergence theorem. Okay, so let's have a look at the 2 sides of the Stokes' theorem here. So the easier side in this case is the d omega side, the exterior derivative of the volume integral. Okay, so let's have a look at d omega. We're going to look at d omega, and we use the same trick that we did over here, okay? So to do d omega, you just apply d to the functions in the front, okay? And you use the change of variables formula for that. Okay, so let's do that with this one here. When you do d omega, the first term you get is dp wedge dy wedge dz. And this dp you can break up into its component constituents. So you can write it out as a function times dx plus a function times dy plus a function times dz. And as before, the dy bit, since when you wedge it with this dy gives you 0, you can ignore that term. And similarly with the part which comes from the dz. Okay, so the only thing that you pick up is the dp dx times dx. That's the only component of dp that you keep. So dp dx times dx. Okay, and similarly for this q, when we look at dq, the only bit that we pick up is the dq dy times dy. Okay, so when you do the dq dy times dy, you've got a dy which dz which dx. I guess you can swap these around. That gives you dx wedge dz. That's one minus sign. And you can swap the dy with that the new dx, which gives you another minus sign. So that gets you dq dy times dx wedge dy wedge dz. Okay. And the final thing that you have is this term here, this dr. The only contribution you get is dr dz times dz. And dz you can, I guess, swap through the dx and the dy. Swapping twice means multiplying by minus 1 twice, so it just gives you dx wedge dy wedge dz. So that we see is d omega. And of course it's beautiful how we see, in this case, this d omega picks up the divergence of this vector field. And the way it's written is it's divergence times this usual volume form here. Okay, so that matches up the right-hand side of Stokes' theorem precisely with the right-hand side, so the volume integral of the divergence that you see in Gauss's divergence theorem. Okay, so let's have a look at the left-hand side of the Gauss's divergence theorem, which is the surface integral or the flux of this omega, this vector field, which I've now written as this 2 form. So I want to compute what is the integral of this 2 form. So the way you usually compute integrals is that you find some parametrization of it so that you can compute it as a usual integral in Euclidean space. So let's suppose you have some parametrization, sigma, from some subset V inside R2 UV to the boundary of D. Okay, so you may need several patches to compute the whole integral, but let's work on one patch at a time. And let's look at the original divergence theorem where we look at the surface flux. So it's given by this infinitesimal element here, f dot n ds. Okay, so let's have a little think about what this really means. So what's n ds? Okay, so here you're parameterizing with parameters u and v, so you'll write it in terms of du dv. And of course this normal times this ds is just sigma, the partial derivative of sigma with respect to u, cross the partial derivative of sigma with respect to v times du dv. And then when you write it like this, of course, the du dv, that's your little area element over there. But this bit here is a triple scalar product, so we can write as a 3 by 3 determinant. Okay, so the first row corresponds to f, so there's your p, q, and r in the first row. The second row corresponds to the derivative of sigma with respect to u. So sigma, remember, tells you for each u and v what the x, y, and z coordinates are. So basically looking at dx du, dy du, dz du. And the sigma v is dx dv, dy dv, dz dv, the third row of this. Okay. So this is what we get in the original divergence theorem, the left-hand side, okay, over here. Okay, so you want to do the surface flux. So what about the left-hand side of Stokes' theorem? Okay, so we want to compute this. Okay, so you want to compute the integral of this 2 form, the surface integral of this 2 form. And to do that, you've got a 2 form omega here, and one way to express it is you pull that 2 form back to v, and it's just the integral of that. And I claim that actually this thing here is precisely the pullback of this 2 form omega via sigma back to your UV space, okay, or UV plane. Okay, and let's see why that's true. Okay, so let's compute sigma upper star of omega and see how that works. It's easy enough. Okay, so here was our omega. So there are 3 terms, and they're all similar. So I'll just do the first term for you. Okay, so what's sigma upper star of p dy wedge dz? P dy wedge dz. Okay, so of course p just comes out, and we just need to pull back the dy and the dz. Okay, so what is the pullback of y and z? So you're pulling the y and z, their functions here, back over to functions over here, right? So of course here dy gets mapped to dy du plus dy dv dv. Okay, that's the pullback of this one form. And what's the pullback of this one form over here, dz? That's just dz du plus dz dv dv. And you're taking the wedge product of those two. So as usual, there's a distributive law which tells you how that works. And the other thing that's crucial to remember here is the fact that when you have du wedge du, you get 0, and dv wedge dv, you get 0. So instead of having 4 terms, you just have 2 now. So let's have a look at what those 2 terms are. Okay, so there's a term which is a du wedge dv, du wedge dv. So let me put that in. Okay, so you get a multiple of du wedge dv. It's always that case. Okay, and let's see what that multiple is. So there's one from this dy du, that's the du, times dz dv, dy du times dz dv. And there's also a dv wedge du term. And dv wedge du is just the negative of du wedge dv. So we have a minus sign times the product of the coefficients there. And the product of the coefficients there is dy dv times dz du, dz du. So pulling back this first term gives you this expression here. Okay, so we want to say that this gives you one of the 3 terms inside here, and let's see how that works. Well, it's p times something. Okay, so let's compute this 3 by 3 determinant. When you expand along the top row, what do you get? You get one term which is p times this 2 by 2 determinant here. And what is that 2 by 2 determinant? You get dy du times dz dv, dy du times dz dv, which is this term here. And you also get this product here, dz du times dy dv, dz du times dy dv. Okay, so that captures the term with p. And similarly, using exactly the same type of calculation, you can show that when you pull back q dz wedge dx via sigma, you get the term that is q minus q rather times the 2 by 2 determinant when you remove this middle column and top row. And there are remaining 2 terms, which is r times this 2 by 2 determinant, which is precisely what you get when you pull back this last term. So at the end of the day, we see that this holds. So what does that mean? So that means that the integral, so here the sigma upper star omega is here, you put it back here. This integral here gives you the surface integral inside the divergence theorem that Gauss gave us. And that's the same as the integral, of course, omega on here, and that's in Stokes' theorem for manifolds. So in this way, we beautifully see that Stokes' theorem for manifolds generalizes both Gauss' divergence theorem and Green's theorem for the plane. I hope you enjoyed this adventure in pure mathematics.